Okay, so thank you. Like Ivana before the break, I will be talking about stochastic programming, but in this case, in particular, about stochastic mixed integer programming. So with mixed integer decision variables in the second stage. I've been doing quite some work in this field, mainly on convex approximations for these type of problems. But lately, we've also been working with one of my former PhD students, Niels van der Laan, on a Bender's decomposition algorithm for stochastic mixed integer programs. And that's what I want to share with you today. And so the outline of the talk, I'll start with a brief introduction into stochastic mixed integer programs. I'll discuss the challenges of these stochastic mixed integer programs. And then I'll explain our new Bender's decomposition algorithm, where we use a new type of what we call scaled cuts. And I'll discuss theoretical convergence and numerical results of the algorithm. And so I'm interested in optimization problems under uncertainty. So problems where we have to make some decisions here and now, while some information is not yet known. Like in finance, we need to invest in a portfolio of assets before we know what the returns on these investments will be. In energy, we need to determine which power generating units to switch on or off before we know what the demand for electricity or even the renewable supply in the near future will be. But also in logistics and healthcare, you face these type of problems. In healthcare, for example, we need to plan surgeries before we actually know the duration of these surgeries. There can be complications in the process, which means that the surgery can take longer or smaller, or take longer or smaller. And so in all these problems, we're interested in making a decision X here and now, while some parameters are random, some information is unknown, and we're trying to minimize some expected function of the first stage and the uncertain random parameters. And so in particular, I want to focus on two-stage stochastic mixed integer programs, which is a class of problems within optimization under uncertainty, where we have to make some first stage decisions X here and now, before we know some of the random parameters. And in the second stage, we can make some actions once we know what the realizations of these random variables will be. And so you can think of X as the strategic or long-term decisions that you make when the future is uncertain, and X as the Y as the short-term or operational decisions that you make when all information is revealed. And so mathematically, in the first stage, we minimize over the first stage decisions, given a linear objective, deterministic linear constraints, but also expected future cost from the second stage. So Q is an expectation over a second stage value function that depends on X and on the random parameters omega. And this second stage is a linear program. So it's an optimization over the second stage variables Y. So we're minimizing a linear cost given linear objective in the second stage. And so this is the same as in Ivana's talk before the break. Now the main difference is going to be is that I allow particularly integer restrictions in this second stage. And so this is now not an LP, it's a mixed integer linear program. Okay, so I want to make several assumptions that are quite standard in the literature. First is that we have finitely many scenarios, each with probability PS. And so for every scenario S, there is a separate second stage value function, which I'm going to denote by Vs. So the second stage value function corresponding to scenario S. I'm assuming so-called sufficiently expensive and relatively complete recourse, which means that this value function is always finite. So the minimization cannot go to minus infinity, but also not to plus infinity, which is the case if there is no feasible solution. And then finally, I also assume that X, the first stage feasible region, is bounded. In practice, this is not much of a restriction because it can still be very large, this first stage feasible region. And so under this first assumption, if we have finitely many scenarios, this expectation over here just becomes a weighted sum with respect to the second stage value functions. Okay, so what's now the main challenge in solving these type of two-stage stochastic mixed-integer programs? Well, if you look at the first stage problem, then if this function q, this expected value function, wouldn't be here, then this would be just a deterministic mixed-integer linear program. Can still be hard, but at least probably much easier than the stochastic problem that we're trying to solve here with the many scenarios that we may have. So in some sense, all the difficulties of this stochastic mixed-integer program are hidden in this expected value function. And in particular, if there are integer restrictions on the second stage decision variables, then this value function q is typically non-convex. And so I have here some examples from the literature. This is the value function of a so-called simple integer recourse model, where essentially we have a one-dimensional second stage problem and only an integer decision variable. So no continuous one in the second stage. And so because the integer can only take, let's say, finitely many values, the second stage value function itself can also take only finitely many values. And this weighted combination, so the expectation, also can take finitely many values. And so you see that q here is piecewise constant. But it's discontinuous. There are discontinuity points in here. So it's definitely not a convex function. And that's also what you see here for a two-dimensional case. Also with only pure integer second stage decision variables, we get a discontinuous, piecewise constant expected value function. And this is an example where we have mixed integer variables in the second stage. And so now it's not piecewise constant, but piecewise linear. But you see we have many, many different pieces in this problem. And so these are the type of functions over which we need to optimize in this case. And if you compare that with the continuous version, so when all decision variables in the second stage are continuous, then we just saw we get a convex value function. We can use LP duality to construct these benders or L-shaped cuts. And here, well, it's not possible because this function, like I just shown, it's not convex. So in the continuous case, we have efficient decomposition algorithms like L-shaped, regularized decomposition, what Ivana just presented, and variants thereof. But in the stochastic mixed integer setting, it's a different case. Still, there have been many authors that tried to come up with decomposition algorithms, Bender's type of decomposition algorithms, when there are integer variables in the second stage. So I've listed just a few of them here on the slide. And if you zoom in on these methods, for example, the integer L-shaped method that was also mentioned in the first lecture, it requires that the first stage variables are pure binary. So there cannot be any continuous variables in the first stage, no pure integers, they need to be really binary only. And if you look at the other papers, you see that this assumption is actually made in several of these papers. There are some exceptions. For example, this paper, it assumes pure integer variables, but pure integer variables in both the first and the second stage, and only pure integer variables. There's this paper on ILP duality by Caro and Tint. It's more general, but it has an intractable master problem because there are many nonlinear functions that are added to this master problem, and in general the master problem becomes hard to solve. And so the goal of our work was to come up with a Bender's decomposition algorithm that has general mixed integer variables in both time stages, so both the first and the second stage. So do not have these specific assumptions on the type of variables in both stages, and also potentially to have randomness in all second stage parameters. Okay, so how are we trying to do that? So This is the idea of our Benders decomposition algorithm for stochastic mixed-integer programs. So remember, we're dealing with non-convex expected value functions over here. So what we're trying to do is similar as in Benders. Instead of working with the real expected value function Q, we somehow, using Benders cuts, keep track of a outer approximation, so a lower bound of these expected value functions that we're iteratively going to improve by adding more and more of these Benders cuts. And so in this picture, the blue lines represent the real expected value function, which is convex. We want to maintain an outer approximation, so a lower bound, that is piecewise linear or polyhedral and convex. And so in the course of our algorithm, we are iteratively going to improve this outer approximation. But what's important is that we want to make sure it stays convex polyhedral, so piecewise linear. And because we do not want to get an intractable master problem. And so the goal is to improve this convex polyhedral outer approximation in such a way that we end up with the best possible convex polyhedral lower bound. So essentially the convex envelope of this expected value function. So how are we doing this? Well, we're going to create nonlinear lower bounds in the second stage subproblems in a very specific way, which I'll explain in a moment. And so using the current outer approximation, and then later transform the bounds that we get into linear or affine optimality cuts for the master problem. And so if you don't understand this, so now I'll try to explain this with some pictures. So we're in the integer setting. We have our master problem over here. And we're going to assume that there are only 3 scenarios, 1, 2, and 3. And in every scenario, we have a different second stage value function. So you can see over here that the parameters of the second stage value function, they change in the various scenarios. So here's a graph of the second stage value function. So you can see it's not non-convex. And I just shifted them a little bit from left to right. So that's the difference per scenario. So they're shifted just left to right. And this is the example. And so what do we do? So in the algorithm, we go to 3 steps iteratively. So first we solve the master problem to get a current best solution. So the solution we think is currently best. We send that one together with the outer approximation that we have to the subproblems. We create lower bounds for the subproblems, and then we send those back to the master problem to update the outer approximation. So step 1, here's our master problem. So remember, we're solving with respect to the outer approximation. So in the master problem, we do not know the real expected value function Q. We only know this dashed line, this lower bound. And so currently we think this is the lowest point. So this is our current best solution. And this solution we send to the subproblems together with the outer approximation. And now we will construct lower bounds for these value functions for every scenario. And so for example, in the first scenario, here's our current solution. And this is a nonlinear lower bound that we could make. And so I want to emphasize that in this case, I'm not allowing any type of nonlinear lower bound, but only those of a very particular form. And because you can see they're partly linear and they partly depend on the outer approximation. So how do they look? The outer approximation is something like this. I can multiply by tau, so by a constant. If it's positive and it's large, it's going to make this very steep. If the constant is small, it's going to become very wide. Then I multiply by -1. So I turn it upside down. So the constant alpha, it makes it larger or smaller. And beta transpose x means I can rotate it. And that's it. That's the type of nonlinearity that I'm allowing at the moment. So you can see that the only king point in this lower bound in this example can be at x bar over here, and that's also where I have the king point over here. But this is what you can get if you have this outer approximation upside down and then rotate a bit and make it higher. You can make such kind of nonlinear lower bound. Yeah, but for the second scenario, now x bar is somewhere more to the left, so I can make a bit of a wider nonlinear lower bound. And in the third case, here, now x bar is to the right of the minimum, but I can also rotate, so I can also make this nonlinear lower bound the other way around. And this is now a lower bound for this value function. And so once I have the nonlinear lower bounds, I know that the expected value function q over here is the weighted sum over these value functions. So I can take the weighted sum over the lower bounds to get the lower bound for q. Yeah, so I can send back the cut coefficients to the master problem, and then I get a nonlinear lower bound, something like this over here. And so I'll zoom in a little bit. So this is the same picture where you see this lower bound over here. And what's important to observe here is that, well, it's tight at x bar. So it's a tight lower bound. And this will actually be the case as long as I construct tight lower bounds at x bar for all the second stage subproblems. Then I also get a tight lower bound in my master problem. Yeah, but what you also see is that this cut is non-linear and non-convex. And I earlier told you that I would like to maintain a convex polyhedral lower bound. So I cannot really use this nonlinear lower bound. I mean, I could now try to optimize over this part, over the maximum of the two. But to do that, yeah, I have introduced some nonlinearity, which I need to deal with in a master problem, or I may need to use binary variables to model the fact that it's the maximum of one of the two. But this makes my master problem considerably harder. So in this project, we try to avoid using any nonlinearities or non-convexity in the master problem at all. So what we've done so far, we have Q. It's the weighted sum over the value functions, which can be bounded by the weighted sum of the nonlinear lower bounds. And in fact, I'm going to use slightly shorthand notation to write alpha as the weighted sum over the alpha s, beta as the weighted sum over the beta s, and tau as the weighted sum over the tau s. And this is this nonlinear cut that you see over here. But that's not the one that I want. I want to make a different one that is linear or affine in X. And we're doing it as follows. We call it a scaled optimality cut. So I'll just try to explain it from the beginning. So starting with Q, I first rewrite this. So I take a weighted combination between Q and Q, weights 1 and tau, and I divide by 1 plus tau. So this is just the same. This is just Q. But next, I replace the second one by the outer approximation. Now in the numerator, I have something that depends on Q and tau times the outer approximation. But if you look at my nonlinear cut, and if you move this part to the left, then you see that this numerator should be bigger than alpha minus beta transpose X. And so based on the nonlinear cut, I know the numerator can be bounded by alpha minus beta transpose X. And I get a function over here that for a given alpha beta tau is linear or affine in X. So I can add it to my master problem and it looks something like this. And so if you look at this scaled optimality cut, then it's linear in X, right? We already saw that. But you can also show that if the outer approximation, so the current dashed line, is equal to the nonlinear cut, so this one over here, that then the outer approximation also equals the scaled cut that we just made. pi. We'll move this to the left, divide by 1 plus tau, and you get exactly this expression over here. So what does it tell us? It tells us that the points at which the outer approximation and the nonlinear cut intersect, those are also exactly the points where the skilled cut should go through. So it's not a coincidence that all these intersection points coincide. This is backed up by theory. I mean, you can prove that this is true. But it also very easily explains that this scaling factor tau is very important. Because remember, what does tau do? We have the outer approximation, we multiply by tau, we make it steeper or wider. But if tau is large, we get a very steep function, a very steep nonlinear cut. So if tau is really large, the nonlinear cut will be very steep, and the intersection points will be really low over here. So the resulting skilled cut will not be that good. So I rather have a low scaling factor, because then my resulting skilled cuts are probably better. And in fact, there's going to be a trade-off between how tight the nonlinear cuts are at x bar and what scaling factor I need to do that. So what we saw was that, well, maybe we need a very large scaling factor to get a tight bound, but then the skilled cut is going to be bad. So maybe a lower scaling factor helps. So there's a trade-off between tightness at x bar and the scaling factor. So that's why we investigated so-called what we call dominating skilled cuts. So where we look for cut coefficients that do not maximize the nonlinear cut at x bar, but the resulting skilled cut at x bar. So remember, this is the skilled cut, so we somehow want to make it as large as possible at x bar. And you can imagine that if I would make this nonlinear cut, which is not tight, then the skilled cut is actually much better and cuts away a larger part of the feasible region. And so formally, to define these dominating skilled cuts, we define pi of s, depending on the outer approximation, as the set of cut coefficients alpha, beta, tau for scenario s, such that the resulting nonlinear function over here gives a lower bound for my second stage value function in scenario s. So pi just denotes all cut coefficients. That gives me really a lower bound or nonlinear lower bound for the second stage scenario s. And then the dominating skilled cut is just to optimize over all those cut coefficients in such a way that this dominating skilled cut is as large as possible. And remember, these alpha, beta, tau are the weighted average over the scenario coefficient, so over alpha s, beta s, tau s. Okay, so at some point during the project we had come up with this definition of these dominating skilled cuts. And then the first two questions I asked myself was, one, can we actually compute them, right? I mean, we want to implement an Bender's decomposition algorithm, so can we actually compute them in some way efficiently? And two, how good are they going to be? So how good of a cuts will they be? So I'll try to start with the second question, so how good are they? And for that we introduced the concept of a skilled cut closure. So this is a theoretical concept, it's not what we want to do in our algorithm, but we're just saying, well, suppose that instead of adding just a single dominating skilled cut, we add all possible skilled cuts that we can make with the current outer approximation. Theoretically, we can construct this, what we call skilled cut closure, which is now just the supremum over all feasible cut coefficients, and then the supremum over all resulting skilled cuts. And so imagine all possible nonlinear cuts that you can make, look at all possible resulting skilled cuts, and just take the pointwise maximum over all of those. That's what we define as the skilled cut closure. And so what we can prove, and that's the main convergence result of our paper is that if you iteratively apply the skilled cut closure, and so you start with an arbitrary outer approximation for your expected value function, and you iteratively apply the skilled cut closure to that, then this sequence of outer approximations converges uniformly to the convex envelope of Q, and so to the best possible convex lower bound of Q. Okay, then the first question. How do we actually compute them? So looking back at this formula, essentially we need to, given a current solution, we need to solve this problem, and we need to solve it over alpha, beta, tau. Those are essentially our decision variables in this problem, determining the cut coefficients. And well, you've probably already seen that this is not a linear function alpha, beta, tau, which is definitely a complicating factor. But also, and maybe even more important, is that because it's not linear, I cannot separately solve this problem per scenario. So this problem at the moment doesn't separate in the scenarios because I really need to know all values of alpha s, beta s, and tau s to construct alpha, beta, tau, and because there's this quotient over here, it doesn't separate. So this looked like a really hard problem. So instead, what did we do? We considered an auxiliary model where we introduce a penalty parameter rho, and then move this denominator to just the objective in a sense. The idea being that, well, we want to maximize over here, so large denominators are probably going to be bad, so we're just going to penalize large denominators. At least the advantage of doing so is that this is now linear in alpha, beta, tau for a given parameter. But it's also separable over the scenario subproblems. So for example, all these scenario subproblems can now be solved by parallel computing, if you want. And so this is nice, but now my favorite property of this auxiliary model. It turns out that if the optimal objective value of this problem equals 0, that then the penalty parameter that you used is actually equal to the optimal objective value in the original problem, and the optimal solution that you get in this auxiliary problem is also optimal in that solution in this problem. So it actually gives you the exact dominating skilled cut, at least if you get an objective equal to 0 in this auxiliary problem. And why is that the case? Well, if the objective value over here equals 0, it means that for all feasible cut coefficients, alpha, beta, tau, and it's important to see that the cut coefficients, let's say all feasible ones are the same, so the feasible regions in both problems are the same. But at least here over here, for all feasible problems, we know that the objective is bounded by 0, and because that's what this value says, it's now upper bounded by 0. But if I move this to the other side, rho 1 plus tau divided by 1 plus tau, it means that the objective over here is now bounded by rho. And because the optimal objective is actually equal to 0, it means that equality holds for some alpha, beta, tau, and then also here equality holds. Which means that for that optimal solution, we also get optimality over here, and the optimal solution will be rho. So that's the proof of that. So knowing this, how do we compute this dominating skilled cut? Well, we only need to figure out when is C rho equals 0. And the big advantage is that rho is a one-dimensional parameter. Independent of the size of the problem, rho here is just always a one-dimensional penalty parameter. So in some sense we can just use bisection or any root finding algorithm to find the correct parameter rho for which C rho equals 0. So we can use bisection or a type of Newton method to figure out when C rho equals 0. And so in this root finding algorithm, we probably have to solve or determine C rho for several values of rho. But because the problem is separable, then every time we only need to solve all the scenario subproblems. And at least now we can do that in parallel. And we couldn't do that when we considered this difficult problem at first. And so what remains to discuss now is only how to solve these scenario subproblems. And you can see over here, it's a linear function, alpha, beta, tau. So the only difficult part is related to this set of feasible cut coefficients. So I'll repeat that one over here. So it's the set of feasible cut coefficients. And we rewrite it as follows. So Vsx over here, this value function, is a minimization over the second stage variables. And the optimal minimum is an upper bound for the right hand side, if and only if for every feasible solutions in this minimization problem, it's an upper bound for the right hand side. So instead of working with this minimization problem over here, we can replace it by a linear objective with respect to the second stage variables, but then this needs to hold for all feasible second stage variables. So we also need to add the second stage constraints. And we have the outer approximation over here. And here we use an epigraph formulation to replace it by theta and say that theta is bigger than the outer approximation. And then we now have just a linear inequality that needs to hold for all values of x, theta, y in a certain set. And this is the set. It's a bit non-standard set because x and y can still be integer. But essentially I consider it as a static robust optimization problem, but with a, let's say, non-standard uncertainty set. And we have two approaches to deal with it. One is row generation, where we do not start with all the constraints in this set, but only a few of those, and then iteratively generate new solutions and new constraints until hopefully we're sure we satisfy all constraints without using all of these points in the set. And we also have a cutting plane approach where we somehow only make the partial convex hull here because only for those points that are interesting essentially. And so summarizing, how does our Bender's decomposition methods work? Well, we go to several iterations. First iteration, we solve the master problem. Second, then we need to determine the dominating scaled cut at x bar. To do that, we need to figure out where C row equals 0. So that's a bisectional row. And to calculate C row, we need to solve these subproblems iteratively. And then we have the dominating scaled cut, can solve the master problem again, and repeat. So that's the outline of the procedure. And so we first tested it on a very small instance from the literature, which is a stochastic program, but it only has a one-dimensional first stage variable and a binary second stage variable. But it's known for having a very large duality gap. And by duality gap, I mean, suppose you would only allow to have linear lower bounds for the second stage value functions, then you will not be able to get a good convex approximation for the expected value function. And so we use these nonlinear lower bounds for the second stage, and in this way we hope to improve these, get a better lower bound for the expected value function. And that's what you see over here. In the traditional cuts, for example, what I mean by benders is just the L-shaped cuts for the LP relaxation, but we also have strengthened benders, Lagrangian cuts. They all have quite a large lower bound because they only use linear lower bounds for the second stage value functions. If you use any type of scaled cut method, then we're essentially able to close the gap. And so using these nonlinear lower bounds for second stage value functions and transforming them back, it really helps to improve this convex polyhedral lower bound. At the same time, we need more iterations and more computing time. So it's more expensive to close this final gap that we want to close. We need more computer time to do that. And that's also what we see when we apply this problem to a capacity planning problem from the Stochastic Integer Programming library. We have several instances that we have solved. We solved them with strengthened Benders cuts, where you can see that we still have quite large gaps in the lower bound compared to the optimal objective value. When we also add Lagrangian cuts, we already get much better lower bounds, so within 0.5%, 1% of the optimal objective value. But it takes significantly more time to compute than these ones. If we add on top of that our skilled cuts, then we even get an order of magnitude smaller, so around 1.1%, but we also need significantly more computation time. So in conclusion, I think our main contribution is that we have now have a Benders decomposition algorithm for two-stage stochastic mixed integer programs that at least theoretically can deal with mixed integer decision variables in both stages and randomness in all second stage parameters. So here we use these dominating skilled cuts, where we use the current outer approximation to make nonlinear cuts for the second stage problems and transform them back to skilled cuts or linear cuts in the master problem. And for future research, I'm also looking into how these skilled cuts may work for multi-stage stochastic mixed integer problems, or how I can combine them with earlier work that I've done on convex approximations for these problems. So thank you for your attention.